We are Team Anveshak, a group of 18 undergraduate students from IIT Madras presenting to you our 2021 Mars rover Endeavour. Owing to the strong performance with Dark Knight in the Indian Rover Challenge 2020 and the constraints placed on us COVID-19, we have opted to retain and further optimize the core subsystems of the previous rover to increase the reliability and robustness this year.
The mechanical module began design from scratch. We aim to explore parameters that we had not considered previously. For the traversal system, we explored various designs and took particular interest in the cramp mechanism. We also considered optimization parameters such as forward-backward symmetry of the traversal system. However, after analyzing the data, we decided to continue with the rocker bogie mechanism, with the rocker and bogie links being made of custom fabricated carbon fiber. We are using balloon wheels this year with modifications made to increase traction. The bar differential was also redesigned with the goal to eliminate play, and the whole system was fine-tuned.
Our 5 degree of freedom articulated manipulator is robust and capable of performing a variety of tasks. Each joint is non-back drivable and actuated independently. The elbow joint mechanism is now replaced with a worm gear set. A newly designed gear train mechanism is implemented for the base rotation. Orientation of motor mounts are changed to allow free arm movement. The end effector is an underactuated 5-bar mechanism with both encompassing and pinching grips. To compensate for the extra degree of freedom, we have repositioned the spring. Now it puts load on the motor only when the object is encompassed. Orientation of the gripper body is changed to allow easy grasping of objects situated above the rover. The complete re-engineering process helped us increase the workspace and reduce undesirable vibrations that make control difficult. We are also implementing inverse kinematics for the arm for its precise functioning.
Our electronic subsystem consists of an NVIDIA Jetson Nano as the main computer and two networks of STM32 microcontrollers connected over CAN and I2C. The CAN bus was chosen for its high reliability and noise resistance. The electronics box houses all the electronic components of the rover, including the Nano and two 24-volt LiPo batteries, which supports rover operations for over 3 hours. A relay-based power distribution board is used, which is incorporated with a kill switch. The PCBs were custom designed to enable modularity in operations for easy assembly and debugging. Our communication setup consists of a directional antenna at the base station and an omnidirectional antenna mounted on the rover operating at 2.4 GHz. It is capable of communicating over a distance of 1 km even in the absence of line of sight. To provide real-time view of the rover's environment, 4 cameras are placed at optimum positions and the orientation of the main camera can be dynamically controlled. A custom web-based GUI is used to set up, monitor and debug the rover easily. Information regarding position, velocity and functioning of the rover are all accessed centrally in the GUI.
For the autonomous task to successfully navigate to the destination location, a control algorithm based on PID control has been implemented, which makes use of data from a GPS and an IMU sensor. To avoid any obstacles in the way, the combined data from a stereo camera and LiDAR is fed to the vector field histogram algorithm, which generates a 2D grid of obstacle probabilities. On reaching the destination location, a spiral search pattern helps to increase the search distance by a radius of 10 meters without compromising time efficiency. The Ross wrapper of ALVAR is used for marker detection. A combination of 3D pose estimation and multi-marker detection is used to identify the gate and pass through it.
The science setup has been divided into two parts, the soil collection mechanism and the onboard laboratory. This year's rover uses an auger coupled with a rack and pinion mechanism to collect soil in order to ensure precise distribution of the samples. The auger digs into the soil, which is then stored in a cup before being dropped into the laboratory for further analysis. Onboard sensors measure atmospheric and subsurface conditions like temperature, pressure, and luminosity. A microscope with adjustable focus is used to observe the physical attributes of the soil and rocks and fossils of extinct organisms. Using these properties, the physical and atmospheric conditions that led to the formation of rocks can be predicted using a database. Our live detection strategy tests for biosignatures like lipids and proteins, among others, to differentiate between samples with extinct, extant, and no life. The preservation potentials of these biosignatures allow us to further estimate how long ago life was present in the sample.